won't go through the entire talk, but that's fine. I'll just cut it off. Like there's like a natural cutoff point.
Yeah, if you want, you can like upload the slides and we can just like have them attached.
Yeah, let me. Do that. Yeah, is there a spot, like an area where I'm supposed to upload the slides in Zoom, or?
Oh, no. We can just do it after. It's fine.
Oh, okay, sounds good.
I think we can get started. I assume that more people are going to be joining relatively soon over the next like few minutes. But okay. Welcome to the, I think this is the 4th February Carper AI talk. Today we have Misha Laskin presenting some of his work related to algorithm distillation, particularly around the idea of like doing in-context learning for RL optimization stuff. And we've had a number of on-off projects at Carper trying to recreate this work. At the moment, things are paused, but we're hoping to pick things back up relatively soon. So we thought it would be in everyone's interest to invite Misha to give a talk. If you want to take it from here.
Yeah, sounds good.
Can you present? Thank you.
Okay, I'm sorry. It took me on, like it put me on mute as soon as I shared.
Oh,
So let me try that again.
no, put you on mute again. I can get asked to unmute. Oh, there we go.
Okay.
There we go.
And it says like, can you see my screen? Or
We can see
not yet?
the slides. Yeah, we can see like which we can't see the presentation, but we can see like the in context learning parentheses Carper.
Oh, okay. You know what? I'm just gonna share my entire desktop then. Okay, did that work?
Yep.
Okay, great.
There we go. Yeah, we can see it.
Perfect. Yeah, well, thanks so much, Lewis, and everyone, Carper, for having me. Yeah, really excited to share some work and just general thoughts on in-context reinforcement learning. And yeah, hopefully it's useful to some of the projects that you're doing at Carper. So I guess to start the talk, we'll just take a step back and think about what does it take to build systems with human level of intelligence. And I know, I guess we're seeing a lot of problems with progress with LLMs and VLMs, but we'll start with something with what looks like an old challenge now. It's still from 2017. It was called the Frostbite challenge from this behavioral and brain sciences paper. But I think this challenge outlined, some pretty concrete and interesting views on what we should expect to see from machines to achieve human levels of intelligence. And in this paper, they introduced this thing called the Frostbite Challenge. Frostbite is a game in Atari. It involves, this little character that needs to hop on some ice sheets and construct an igloo while avoiding a polar bear. And what's interesting about the Frostbite Challenge is that it's kind of a microcosm of general intelligence. And I think it's still quite relevant today. So the Frostbite challenge outlines two things. One is a data efficiency, which is learning how to play new games in 15, 20 minutes of real-time gameplay. That's on average how quickly humans pick up new games in these kind of 2D Atari domains. And then the other thing is generality. So generalizing to new games and adapting very quickly to new instructions. And at the time, this was plotted in the paper on the data efficiency, where in the star shows how efficiently human solves this game. On the x-axis, there are a number of gameplay hours. On the y-axis, the Frostbite score. And within a few minutes, a human is able to pick up the basics of the game. In 20 minutes, get to parity with DQN that's trained for 200 million steps in this game. On the other hand, the DQN learns slowly. It takes around 500 hours of real-time gameplay to achieve the score. So there was this big data efficiency gap. And despite these new benchmarks coming out like Atari 100K or RL algorithms continue to improve in data efficiency, I don't think this gap is really, it's not even close to being closed for the entire Atari suite, and let alone other more realistic, interesting domains. The second challenge in the Frostbite challenge is generality. And this is an excerpt from the paper where they propose to take the instructions for the reward for the default Frostbite game and then change it to things like getting the lowest possible score, get the closest to some increment, beat your friend who's playing next to you, but just barely, not by too much, don't embarrass them. Like these sorts of directives are actually things that now seem familiar with language models, but still we don't really have agents that can do this in Frostbite. So it's the same thing as a data efficiency challenge, but with new instructions. So what you're saying is that you want to data efficiently pick up new tasks. So that is adapt to different rewards. So today's best RL systems are still far from solving this challenge. And the closest systems with generality capabilities that we would like to see here are large language models, but of course they don't apply in this modality because it's beyond text. And so kind of switching gears to where we are today, if we look at how deep learning versus deep RL research has progressed over the last 10 years, like very broadly, I see it as a increase in flops on the x-axis for both sides, but with the two communities kind of targeting whether it's something that was desired or not, but targeting kind of different capabilities. So on the deep learning side with large language models, VLMs, what's emerged is you exchange flops for generality. You go from task-specific models like seek-to-seek to generalist models like the GPT family of models. On the RL side, there's also been an increase in flops, and we've gone from and we've increased in competence. So we've gone from agents that do fairly well on some games to agents that completely achieve superhuman performance in hard environments, but they're kind of masters of one trade. They're only able to do this for one task, and to get it to another one, you need to retrain the full algorithm. So this is kind of more precisely what I mean by this. There's been a lot of progress in RL, especially, on the Atari benchmark and beyond that. On the left side, there's a table of different algorithms, starting from DQN and ending with mu0 and Muesli style algorithms that went from roughly 80% median HNS to 1,000% on Atari. So this is 10x better than a human would play it. But these are still very narrow algorithms. You cannot transfer from breakout to Frostbite and so forth. Similarly, there's a new algorithm called DreamWeaver3 that was introduced over the last couple of months. Very impressive single GPU RL algorithm, and it achieved this. It solved the diamond challenge in Minecraft, and I think that's really impressive and amazing. But it's still a single task algorithm, so it's kind of almost like a priority as a field. And what the benchmarks were designed for was for this sort of single task competence. On the other hand, what we're seeing with LLMs is that there are these generalist systems. If you go to the OpenAI playground, you have all of these pre-filled templates that allow the LLM to do various different things. And I think this tweet by Karpathy captures how general they are, is that you can, LLMs are whatever you prompt them to be. They, you know, they're probably the most generalist systems that we know to date. And the main difference, I think, is that we've gone from in-weights learning in LLMs and VLMs to in-context learning. So rather than an RL algorithm that's been trained to kind of memorize a task and its weights, the learning has gone from the weights to the context. So by giving a task description and some examples, your language model can learn from that context how to complete or achieve the task. So what I think is that we want to move on to like similar systems in RL as we have with the same level of generality, where you can kind of prompt them to do whatever you want them to do. And so just to answer the question of, what is in context RL? Well, it's just RL, but we want to do it in context. We want to build these general systems. Or, jokes aside, we really want to build agents that can self-improve in context. So right now, we have agents that can self-improve in the weights through many interactions with the environment. That's what RL algorithms do. They're quite good at it. But in order to have generalist systems, we want really one agent that can self-improve on whatever task you give it. And I believe that the way to do this is by shift learning in RL from in-weights learning to in-context learning, just as it has happened with language models and VLMs. So moving from the kind of LLM domain to how we typically describe reinforcement learning systems, what I'm going to be showing in the remainder of this talk is going to be taking the exact same RL formalism, where you have an agent that's interacting with the environment by dispatching actions. It observes state, it observes rewards. That's not going to change at all. So this is we're going to be considering the normal reinforcement learning setting. And again, the same setting where we want to induce reward maximizing policies from our models. So there's typically this is done by having a value function like a Q function, which estimates the future sum of rewards in your agent's lifetime, and your agent tries to maximize this to maximize its rewards or returns over the lifetime. And we're going to be considering the same exact setting, but now we'll want an agent to do this not for a single task, but for a wide range of different tasks. And to make the distinction a bit clearer, in terms of what we mean in terms of in-context learning versus in-context RL, so in-context learning is kind of this example that we brought up before with the task description and some examples. In it, a human specifies a prompt, the language model completes it. There's mostly no reward maximizing behavior. Sometimes there is. I have seen examples where language models self-improve, but it's definitely not the default, and it's unclear how general those self-improvement behaviors are. Whereas in context RL, we'll want an agent to set its own prompt by interacting with the environment. You might be able to seed the prompt with a demonstration or with a human injected prompt if you want to, but you want an agent that will improve itself even if it starts with an empty prompt by maximizing rewards. So how do we build such generalist agents? I think we'll do it with in-context RL, and I'll be talking about both a series of works that led up to the algorithm distillation paper. We'll also talk about algorithm distillation, and if time permits, there's a recent adaptive agents paper from DeepMind that is also quite interesting on the same topic. And I see that there are two paths to doing in context RL. The one that I'm mainly going to be describing in this talk is turning RL into a language modeling problem. So this is kind of taking the data-driven RL approach to building generalist RL systems. And the key insight in data-driven RL, which I'm sure you've heard a lot from Sergey's talk, whether it was, I think, the previous week or the week before that, but instead of doing continual RL, where you have an agent that interacts with the environment in a continuous loop, you change this to an offline reinforcement learning problem where there's a big data set of past interactions. you then you distill a policy from that data set by training for many epochs and deploy that policy to new scenarios. And a lot of offline reinforcement learning deals with fitting value functions to offline data, but we'll be talking about a different approach that kind of does more, I guess, is more akin to imitation learning than it is to learning value functions from offline data. So to start, we'll talk about the decision transformer paper, which was titled Reinforcement Learning via Sequence Modeling, even though I'm going to argue that the paper didn't actually do reinforcement learning, but this paper and others that came out concurrently, like Trajectory Transformer, showed some interesting things. And in these papers, the RL problem is treated like a sequential prediction problem. So you have a sequence of reward state action tokens, and your agent is tasked with just predicting the next action, conditioned on the state and returns that came before. What this allows you to do is it allows you to extract a return condition policy from your offline data, such that when you condition on high returns for your downstream tasks, your agent will execute a policy to the best of its ability to achieve those returns. And the interesting insight from this paper was that this kind of return condition imitation learning approach rivals common TD learning methods and outperforms behavior cloning for offline RL tasks. But the limitations of the decision transformer, well, one, it was still single task, so you still have a single agent trained for each one of these environments. But I think the bigger limitation is that it couldn't improve itself. Kind of what you see is what you get. So in these plots, they show the target return on the x-axis and the score that's actually achieved by the policy that you dispatch. The green dotted line means kind of what an oracle would do. So if I ask it to achieve a return of 100, the policy would output a sequence of actions that would achieve return of exactly 100. And the decision transformer, what you want it to match this green line as much as possible. And you can see that it does that for some environments, but not all. And certainly in the high return regimes, the policy does not achieve the return that you ask of it. It achieves a lower return. So for instance, this Walker environment, there's a gap here between the blue and green lines. And what that's telling you is that this agent, you ask it to achieve a return of 100, it achieved a return of 50, and that was it. It couldn't really get better. It couldn't improve itself. What we want so this is kind of doing in-context policy learning, but it's not really doing in-context RL, because an in-context RL agent would be able to improve itself. Moving on to a paper called Multi-Game Decision Transformer. This was a very similar paper to DT's.
Quick question, sorry.
Yeah, of course.
About the decision transformer, what's the intuition for why it's able to do better than behavior cloning?
Yeah, it's a good question. So I think that it's due to this, like you're conditioning your policy exactly on the return that you want, and you in a sense have like a wider distribution of data that you modeled. So in these data sets, like when you actually start filtering behavior cloning, it might be a small data set issue. That is, like if you filter the data sets based on the ones that achieved higher returns with behavior cloning, you actually get a pretty small data set. And so behavior cloning might just be overfitting. So if you were to train, let's say, like on a very large, massive data set, maybe it would be sufficient to just filter it, kind of return filter it. And maybe that would give you similar performance to decision transformers. But if you just have, but if you don't, or have like a very large diverse data set, then you can just get this by return conditioning.
Thank you.
So moving on to multi-game decision transformer, the TLDR of this paper is it showed something interesting. It showed that DTs can generalize to play multiple games within one agent, but still no self-improvement operator. So in this paper, they pre-train on a large data set of both non-expert and expert trajectories, including multiple games in the training set. And then to play new games, they fine-tune the MGDT on this data set of new games. The architecture looks almost exactly the same. There are some details that are different between this and the DT paper, such as patching up your image into and treating each patch as its own token. And the way return modeling is happens is a bit different in this paper, but ultimately it's a very similar architecture. And in it, they showed that you can have one transformer that plays multiple games roughly at the level of single task agents that are also trained offline. Yeah, but I guess a caveat on this paper is that it's the same results that held with decision transformers that they couldn't self-improve were also true here, which is why it was required to fine-tune the MGDT on new games rather than just dropping it in a new environment and having it self-improve until it maximizes the returns. Moving on to another paper in this progression called Gato. This is a paper from DeepMind. This was kind of a scaled up example of a multitask decision-making agent. So this is actually kind of going back to why not just do behavior cloning on better filtered data. That's exactly what this paper did. So in this paper, there's no return conditioning. It was just behavior cloning on correctly filtered data. This paper really scaled up the number of environments that were that were distilled into a single transformer. So there was this playroom environment, robotics, Atari. There was a chat environment, and many others. And the main insight of this paper was to just tokenize everything, like all your modalities, just tokenize them. You have different tokenizers for all of these, but the transformer ends up just kind of treating, they kind of are all subsets of some bigger superset of a token vocabulary. And you apply an imitation learning loss to your data, just a cross entropy loss, same thing that you would do with LLMs, and you kind of get this action server. So one limitation to this paper, Gato, is that it required it usually required like a fixed prompt. So if you want to apply this thing to a downstream task, you have to give it an example of what achieving that downstream task correctly might be. So it's kind of like a powerful general behavior cloning agent, but it's still not a self-improving agent. But nonetheless, this behavior cloning agent was able to show up to human level, maybe a bit lower performance across any task. So it is moving in the direction of generality of the Frostbite challenge, kind of going from single task RL agents and producing multitask ones, even though this is a behavior cloning paper primarily. Yeah, I'll skip this slide, but it was kind of interesting that this the modalities that Gato captured. It was able to both do control tasks, but then also do Q&A and image captioning. So it was really, the generality was really cross-domain and modality generality. Okay, so by this point, I've shown 3 examples of ways in which transformers were used to extract policies from offline data. But all of these methods ended up producing just policies that are fixed. So policies that cannot improve themselves. And motivated by these works, the kind of question we pursued with this algorithm distillation paper was whether transformers could also reinforce and learn in context, not just learn and imitation learn in context, but also reinforce and learn. And this is the paper that we wrote in context RL with algorithm distillation. And in it, the motivation was just taking what we're seeing, that's what's happening with in-context learning from other models, like we now see in-context learning produce generalist agents for LLMs, VLMs, and reinforcement learning models. But the issues with these models is that they don't adapt, I guess, autonomously to new tasks out of the box. So if you want this thing to solve a new task, you need to either provide a prompt manually. If that still doesn't work, maybe you'll fine tune the model or use preferences to align it with whatever task it is that you'd like it to do. Or maybe you'll just retrain a larger model with more data and hope that some additional capabilities emerge at scale, which they've certainly been shown to do. And you might think, well, wait, I thought transformers could also do RL like these. But by now I've argued that DTs cannot, but I just want to make this point a bit clear. The inputs to a decision transformer is you have an offline data set, it's a replay buffer of some agent. And crucially, what's interesting is that data actually contains learning signal. So the replay buffer of an agent is everything it's seen over its lifetime, assuming that you don't, assuming that you didn't discard any of the data that it saw. But even though you have this data set of everything an agent saw, so it has kind of this learning signal from when it went from dispatching random policies to expert ones, the thing that you fit is actually a return condition policy, this pi of A condition on S and R. So there's nothing in this training objective that would induce the sort of learning behavior that we desire. And the reason for that is because even though there's a lot of learning data in the offline data, the context that decision transformers and other papers used to fit this data were quite small. So if you have a small context, then it won't capture, there won't be enough learning that happened in the context for you to actually be able to extract the learning signal. And this is the problem we addressed in algorithm distillation. The approach ended up being quite simple, kind of, the short version of this paper is, well, what if we do decision transformers with longer contexts? That's pretty much it. So you have a data generation step where you capture n replay buffers. So many replay buffers of RL algorithms being trained on single tasks. So each one of these orange blocks is the entire history of learning from some RL algorithms. In this case, we had some off policy and on policy ones, like we had a DQN Q lambda agent and A3C agent. And we also distilled some bandit specific agents like UCB. But the important thing is that it doesn't matter which algorithm you use, it can be a mixture of algorithms, but you need to save the full learning histories. And you want to do this across many tasks. And once you have this thing, you fit a causal transformer just like you would with a decision transformer, but the context or what you're conditioning, this action prediction on, is a much longer context than DT is considered. So you want contexts that capture where enough improvement happened for your transformer to pick up on that when it's predicting actions. So usually that means cross-episodic or multi-episodic contexts. And another interesting detail is that you might notice that there's no return conditioning going on here. We're feeding in the exact sequences that the agent saw. So observations, actions, rewards. And the reason you don't need return conditioning is that if the agent has distilled the learning behavior from the training data, then it will kind of implicitly be doing return maximizing behavior already. You can certainly try to make it better by conditioning on the return, on the desired return as well, which we didn't do, but can be done. But you don't actually need this. You can model just the raw data that the agent saw during its lifetime. So once you model this with a cross entropy loss that's just imitating the actions, you get something like this. So
Misha,
yeah,
sorry, do you mind if I ask a question real quick?
Yeah, of course.
So in the inputs that you use for algorithm distillation, do you put the episodic termination signal as part of the tokens as well? Something like done or termination, truncation, that sort of thing?
Yeah, it's a good question. So in this paper, we didn't, because the episodes were all fixed. They had fixed termination.
Mm-hmm.
So in that sense, the transformer can kind of pick that out implicitly. Of
see.
course, so there are two things. Like first, yeah, I think it's mainly that the episodes are fixed. And yeah, but you could you could add a done token, and you probably would want to if you had yeah, if you had agents with varying episode lengths, and yeah, we've done this as well, and it also works. It wasn't in this paper, but it's, yeah, I guess given these results, not too surprising that would also work.
That makes sense. Thank you.
Yeah. So after this is the what I kind of just described was the pre-training phase for this method of in-context RL. So after you've pre-trained it, you can then deploy a transformer with fixed weights, so you don't change the weights anymore, and you deploy it in an environment on some new task. And in this case, we deploy it on the same environment that it was trained on, but on holdout tasks. Even though the tasks are holdout, they're still coming from the same distribution of the tasks the training ones came from. So the context is initially empty. The agent interacts with the environment. It puts the first tuple of observation, action, reward in its context, and then it just continues doing this. So I guess the main thing is that the context here is empty, and the agent is filling up its own context by interacting with the environment and selecting the next action condition on this context. In this case, this environment is this water maze environment, and the way the water maze environment works is that it's based on this psychology experiment, the Morris water maze, where a mouse was put in a pool of water, and there's some platform that's hidden in this pool of water, and the mouse has to swim and kind of find it, but it can't see it. So once it gets to the right location, the platform elevates, and the mouse can kind of get on it and prevent it, avoid drowning. But the important thing is that you can't see that platform, and that platform. So with each trial, your mouse has to explore and then remember where the platform was. So the platform's location is kept fixed across trials, but the agent needs to remember where the platform is. So when you deploy AD in this water maze environment, you get curves that look like this. So in red, that's algorithm distillation. On the x-axis, you have environment steps, on the y-axis, return. And it just looks like a normal kind of classic reinforcement learning curve. So the reinforcement learning problem is exactly the same, but the way we solved it is different. And in particular, there are no gradient updates happening at this point. This is all being done in context. The green baseline, expert distillation, is closer to the family of models that we explored earlier, like decision transformer, MGDT, and Gato. And you can see that it kind of flatlines. It doesn't really learn how to solve this task at all, which is consistent with kind of the rationale that we put forth earlier. And one thing to note that's kind of interesting is that the source algorithm, this is the data that algorithm distillation was trained to distill, is in blue. And we can discuss this in a bit, but it's kind of interesting that algorithm distillation is solving this task more efficiently than the source gradient-based algorithm. And finally, we have RL squared, which is the gray kind of oracle line. This is another way of doing in-context RL, but requires kind of 1 billion, in this case, training interactions in order to achieve this. So we can discuss RL squared as well, but in this case, we used it as kind of an upper bound for how much do we think, how well would a meta RL agent do, given that RL squared kind of solves this task pretty optimally. And the same thing, kind of the same style of results held in all these different environments that we tried on. The environments where, water maze was definitely the most kind of visually complex environment, and it's not that complex. So I guess these environments were more, I guess, academically motivated to be hard, kind of either hard exploration problems, or all of these require memory. Basically, you can't solve these without having a memory. But expert distillation, which has the same memory size as algorithm distillation, is not able to learn these tasks either. So you need both a memory, but then you also need to know how to do exploration and credit assignment by just looking at your context. And expert distillation can do credit assignment once it sees a reward, but until it sees a reward, it cannot really explore, which is why the scores are so low. Some observations from this work, like this ability to learn to do reinforcement learning in context only emerged with sufficiently long context. So this ablation shows what happens when you go from a context length of 20 transitions to 200 transitions. And you can see that there's a monotonic improvement depending on your context length. So that's just kind of to validate that the amount of history you put in your context matters a lot for the ability of your agent to do credit assignment and exploration. The other interesting thing, which might be more relevant for for things related to LLM training, is that algorithm distillation does quite well when conditioned on demonstrations.
Hey, how's it going? Oh,
Was that a question or?
No, I think someone just unmuted their mic on accident.
Oh, okay, no worries. Yeah, so when you condition algorithm distillation or expert distillation on suboptimal policies, you get these results. So on the right, we have expert distillation with from 5% to 95% optimal. And when you condition it on that policy, you can kind of see that expert distillation basically just maintains the quality of that policy. It might improve slightly, but really it just maintains the policy that came in. Whereas algorithm distillation takes whatever policy you had coming in and is able to improve it until it is optimal or near optimal in a pretty data efficient way. The other thing that's kind of interesting is that AD learns a more data efficient policy as an in-context RL algorithm than the one that generated the source data. And this was true for a number of reasons. In the previous plots I showed, that difference was quite drastic. And the reason for that was there are kind of some confounding factors. So one is that in RL, you usually train these multi-stream agents. So where you have maybe 100 actors going in parallel. But when you distill these into a transformer, then you're kind of distilling the reason these RL algorithms are inefficient is because they have 100 actors or so, let's say, exploring in parallel. But once you distill that into a transformer, you get kind of, near 100x gain by default, just because you've distilled a multi-stream into a single stream algorithm. But in this experiment, we just did a kind of apples to apples comparison where we had a single stream source algorithm. So you don't get any efficiency from distilling a multi-stream into a single stream transformer. Here you have like a single stream A2C, and when you distill that into a transformer with AD, you still get a much more data efficient algorithm, which for other reasons, but I think this is kind of less well understood why by imitating an algorithm, why you might get something that's more data efficient. But one thing to note is that AD doesn't actually take in the full history of learning. It only takes in a context of size, let's say 4 episodes or something. So it's not exactly like, maybe if you distilled the full history, it would be as efficient as a source. But by truncating the context, you might be kind of biasing it to exploit a bit more than it would otherwise. So yeah, I think we're 38 minutes in. There's another path to doing in-context RL, which I won't cover, but it's kind of more the RL squared path. And in this path, like what we just did with algorithm distillation is we turned in-context RL into an imitation learning problem. But you can also get in-context RL by kind of doing multi-episodic RL at scale. And maybe just to show kind of what I mean by this, and then we'll have some time for questions, is like when we have normal RL, this is what we're doing. We have an episode. RL is trying to maximize the sum of rewards over this episode. And you learn a policy that takes in an observation and outputs an action that's maximizing returns. So it's maximized rewards over a single episode on a single task. Meta RL, or this kind of second path to getting in-context RL agents, is doing something really similar. But instead of a single task, you have many tasks. instead of maximizing rewards over one episode, you have many episodes. And your policy, instead of being conditioned on the observation, it's conditioned on the history of everything that came before it. So in particular, like if you have K episodes, you're trying to maximize the returns across all those episodes, and you're kind of treating those as one big episode. So when you do the summation, you just have K times N, and you're discounting from episode 1 to episode K, and attaching a reinforcement learning loss to this. And with memory, what will happen is that to optimize this problem, the agent will first find, some kind of general exploration strategy that doesn't utilize memory. It's just kind of a general exploration strategy for getting decently high rewards across these episodes. But once it's done that, the next thing that it kind of unlocks to maximize rewards is starting to use its memory to look at previous episodes and see what it did in order to eliminate hypotheses for which tasks it might be doing. So this is what the RL squared baseline is doing in algorithm distillation. And if you're interested in seeing a scaled up version of this, I would refer you to the adaptive agents paper that came out of DeepMind recently. But yeah, at this point, I can pause the talk and maybe we can discuss it.
Thank you very much for the talk, Misha. Yeah, so people can start asking questions. We can do either in chat or people can just unmute themselves and ask.
I can go ahead. Thanks for the talk, Misha. This is really great. I was curious if you could share more details on the sequence length. So you mentioned that that you have to see, let's say, 4 episodes or something for the agent to sort of to in context learn. I was just wondering, how long is the sequence length? Is it like you need to see 1,000 observations before it starts improving, or is it like much faster than that?
Yeah, it's a good question, and it largely depends on the size, kind of both the algorithm that you use to train and the size of the length of episodes. But in our case, in these simple tasks, the episodes were, let's see, I think 200 transitions was 4 episodes, so 50 steps per episode. So you actually start seeing in context RL emerge after only, let's say, in our case, like even after, let's say 30 or something transitions, like half an episode, you start seeing in context RL emerge, but it performs quite poorly. And you usually need a couple of episodes at least for it to start kind of hitting optimal behavior. But it is rather problem specific.
Mm-hmm. I see. Thanks.
So I don't know if you're allowed to talk about this yet, but when we spoke at NeurIPS, you said that there was some interest in using like context distillation for much larger context window requirements, like for RL problems that might require like a 30,000 token context window. Has there like been any update on that, or is there anything that's like expected or anything that came out that we may have missed?
Yeah, so yeah, definitely can't speak to things that are ongoing. But I think that, so this like large context problem is not unique to algorithm distillation. It's, I think, kind of a general problem for both in context RL and in context learning. And yeah, but an interesting paper to look at, if you haven't already, is this adaptive agents paper, where they took RL squared and scaled it up to much more interesting environments than the ones we considered in AD.
Mm-hmm.
So that might be, and there weren't, I wouldn't say there were like massive architectural innovations in that paper, but there were some tricks around getting transformers to work for RL, and they ended up using this kind of combined, like transformer XL. It's a combination of a GPT-like transformer with an RNN.
Mm-hmm. That makes sense. I'm wondering, like, if you want to deploy a model RLHF with algorithm distillation, but you want to keep the benefit of a really long context window, but you need demonstrations that take up a huge portion of this context window to effectively deploy it. Like, there has to be like some weird compression mechanism that happens in order to try and fit everything. it's a really tough problem because
Yeah. Yeah, I think that with getting, yeah, I mean, getting like in context RLHF, well, I guess it depends on, like, my understanding of most of RLHF is that it's kind of like bandit-like in the sense that it's, I mean, I guess, yeah, you guys know a lot more about this than I do. But my understanding was that you are effectively, you have, you output some sequence, you like then have a like reward that conditions the quality of that sequence, and that's really your signal. So it's a token that models like the quality of a sequence. And so it's in a sense like it's like a bandit problem. It's not that you have like a reward attached to each token. And so maybe like there, yeah, I guess I'm curious, like, have you guys tried just kind of decision transformer, like, ideas for RLHF?
yeah, there was a few papers that came out on that basically over the last like few weeks. There's the hindsight paper from Berkeley, and then
Yeah.
there's the pre-training with offline RL paper that came out from NYU, I think like last week.
Yeah.
So
Yeah.
those look really promising, but they require you to label your pre-training data set in ways that are very unnatural.
I see.
And so it doesn't really scale to the level that you need to do an actual large language model. It's very much for toy examples.
Yeah. Yeah. And do you think so? I guess, yeah, is a limiting factor the like how much of this improvement history you can put in your context?
Yeah, how much of the improvement history you can put in this context, and then how much of your data you can actually annotate with rewards, and can you get a reward that's like actually cross domain, and how do you quantize this reward in a way that makes sense to the language model without losing on it? There's many issues to applying decision transformers to language modeling, and I don't think there's any good solution yet. We're getting there though, I think.
I mean, Luis, I don't think, Champ hindsight paper, that's very easy to annotate with our collection of supervised data set, right? And but we can debate more about that later. I actually want to ask Misha some more technical questions. But maybe I'm just coming from language models. I don't know this very much. So in the second to last work you presented, which is, I mean, the main long context work you presented, and you said that everything is tokenized. So the state of the task is tokenized, and presumably there are some rewards that are integered. Like, this is not a pre-trained language model, right? You start by random initialized weights.
So I think in that work, I think the language model was pre-trained, and I think maybe some of the vision encoders were pre-trained as well.
How do you tokenize like the task, whatever, not Atari games, like the Island Fish, whatever game? Like how do you tokenize that into useful tokens for your model?
Yeah, so I guess there's like there's like the image tokenizer, which is just can be like a patchwise tokenizer, or I mean, in the same way that it's tokenized for vision transformers or something like this. So you can have patchwise tokenization. I think the one that is, I mean, yeah, I guess a tokenizer is just like converting your vector input to some kind of, to a vocabulary. So you can use, like, I mean, won't work well, but I guess you can use random networks in principle. And I think the issue with Gato was there was a big issue around the action tokenization. So yeah, like ultimately, like the paper didn't show really strong generalizations to the kind of new tasks. And I suspect the reason is, like, one of the reasons is that there wasn't enough diversity around action spaces around the different tasks for you to be able to generalize to something with a new action space. So I guess, like, I think the issue was less maybe around the tokenization scheme and more around just data diversity,
right,
for that problem.
Okay. And since you mentioned the need for long context, like, the rewards, if that's just an integer, like that could be 2 or 3 tokens, but like, is the state space super, like, does that require a large number of tokens, or is it like the actions? So that's really hard.
Yeah, so I guess in our case, the way we tokenize the images was just with a CNN encoder. So in that case, like an image was just 1 token. But again, like it's not necessarily like a high quality token. But the nice thing is that you don't, like, we're just using images to condition. Like it's not a world model that's predicting images. So and the problem was simple enough where that tokenization sufficed. But for instance, like in MGDT, they had to, tokenize an image by patching it. But then if you patch an image as a 9x9 or 3x3
Yeah.
patches, then you like added, you've 10x your tokens so you have to have a good reason to do it.
And is there a large vocabulary size for your image state token?
So the image it's not tokenized discretely because so it's just a continuous embedding.
Just a vector. Okay.
But you're not predicting it. You're predicting the actions which are discrete. And in principle, you can predict like a continuous action space as well, but that, cross entropy is magic. So you want to discretize as much as you can when you're predicting, when that's the thing you're predicting.
Okay, sounds good. Thank you.
Hey, Misha. So I want to start my question with a like making sure I even vaguely understood the method. So you pass in episodes that are sort of improving over time because they're being generated by something that is trained, and then you sort of notice the trend of what it looks like to improve, and you imitate it or keep on going with that.
Yeah, so you're just doing imitation learning. So, but as you said, like your your training data has learning happening in it. And if you're doing imitation learning on, let's say, on very short context, like suppose it's just like using one observation to predict an action, then you wouldn't pick up any of that kind of learning signal because because it's just not in your context. You can't make that prediction problem. And so you'd have like a really bad predictor because the same observation produces different actions throughout training. So like when your agent is random, an observation will produce some random action. When your agent's optimal, the observation will produce like a low entropy, optimal action. But if your context is too small, then your agent can't distinguish between these two modes. And so the imitation learning loss will be bad. But if your context is large, then the agent has to kind of infer where it is along training. Like, is it by looking at its context, like, is it a random agent right now? Is it like an optimal agent? Is it somewhere in between? And by imitating by imitating this learning history, it will be trying to output the kind of next best action, like it would have in the training data.
Okay, yeah. So when I train my reinforcement learning algorithm, sometimes we get one of these and then one of those, and then back to being good. I feel as though like RL training is often quite unstable, even if it tends towards success. So did you find that stuff like that was a problem? I could imagine it sort of being like, like if you have 5 bad episodes in a row, then you just sort of forget, you have no more good context, and you sort of go off the rails.
Yeah, definitely. So that definitely happens. And, our data sets had, I forget how many, but maybe like 1,000, like, I think a few thousand actually tasks in them. And so we did do some filtering. We kind of have in the implementation section, we have some details on that, but it's like buried in a sentence somewhere. So we did filter things out. Like sometimes like their bad seeds just don't learn anything or don't learn stuff for a while, as you mentioned. So we just kind of threw those out. And it turned out that we kept the majority of the trajectories, but we kind of pruned out the bad ones. So with this kind of method, that's certainly an issue. Like you can get polluted data if you're not careful about curating it.
Cool, thanks.
Sorry, what was this recent Facebook paper that you mentioned about reinforcement learning agents?
Oh, yeah, adaptive agents.
From
Let
Facebook?
me, it's from DeepMind, but let me find it for you. And
I
I'll
think
just-
I posted in the chat. Is that the one?
Oh, okay. Yep, that's it.
Yeah,
So-
as I mentioned after that, there was a paper from Facebook in the same vein.
Which paper? I'm not sure. Maybe I'm not familiar.
No, you mentioned it. I mean, it was, maybe I was wrong. Okay, thank you.
Yeah, I do think that getting this stuff to work for language models is very tricky because of both kind of context lengths and yeah, and we dispatched like 1,000 RL agents, maybe more, like thousands of RL agents to generate data, and it generating, dispatching thousands of language models in parallel may not be the thing to do. So yeah, I suspect that if we want to incorporate it, these ideas more into LLM, like getting the sort of in-context adaptation from LLMs, it would require, yeah, some kind of pragmatic shortcuts around, it might be hard to get like a purist, like algorithm distillation implementation working in with LLMs.
Yeah, I'm under the impression that it's not entirely feasible. But to that end, we're also trying to get Muesli working in TRLX. That's close to this year. He's indirectly working on that. And we're hoping that if we get Muesli working, Muesli is very, very expensive, and algorithm distillation is much less expensive, meaning that we can get the benefit of Muesli without actually having to use Muesli.
Yeah. Yeah, and I guess depending on your training setup, you could also, like, if you do Muesli or you maximize rewards over multiple episodes, then you get RL squared. Because Muesli has memory baked in. Well, it has it with an LSTM, but as the Ada paper used Muesli with a transformer Excel backbone, and it actually didn't, this sort of in context RL didn't work with an RNN. Like you needed the transformer backbone. So that's another way it could be done. Like it could be done in an online way, like rather than having to like collect data, distill it. Like you could do multi-episodic Muesli.
That's really interesting. I never even considered that you could just directly use Muesli rather than having to go through the algorithm distillation component.
Can you maybe say a bit more on why you said, like, what kind of memory is needed for RL square, and how, and this is like a neural module that's separate from the transformer itself?
So I guess for like RL squared works with RNNs, and for simple problems, kind of for like in algorithm distillation for the problems we considered, the transformer variant actually did slightly worse than an LSTM. So we just had we used the LSTM baseline instead. But RL squared has been really hard to scale up. Like it was, I think first paper came out 2016, and this adaptive agents paper 2013 is the first paper I would say that really scaled this method up successfully. And part of it is that yeah, our RNNs are just get pretty finicky at scale and have like memory issues where they actually don't retain memory that well, which was actually present in the original RL squared paper. So, and there are a number of things that most of them, many of them may not be relevant to training LLMs or doing this like adaptive LLMs. But there are a few details that they needed to get right, which was using a transformer Excel instead of an RNN for just the Muesli backbone. In principle, maybe you could even make that your GPT transformer. Not sure, would have to think about it. Yeah, you probably could just make that like, you could probably just use the same backbone and attach some like policy heads instead of like training a separate transformer. And then there were some other ideas around generating a curriculum of tasks. I don't know how useful that is for LLMs, because that was in RL, the issues like more like when you're starting off with nothing, there are all these tasks that are out of reach for your agent. So how do you smartly select which tasks your agents can currently do, but are still interesting? Yeah, and what was the last thing? Let's see, I actually have it in my slides somewhere. Oh, well, and I guess, yeah, and just using a state-of-the-art agent. So like they trained this Muesli agent for 40 billion steps. So like, and Muesli is pretty efficient. So like you have to, yeah, train these for a long time. So that might be a bottleneck that, but maybe not, because LLMs have a really good initialization. Whereas, so I think most of RL squared, like exploration, is getting out of this terrible random initialization that it's at.
Well, we have pretty terrible initialization too, except they're, you know, pre-trained for trillions of tokens.
Yeah.
In terms of types of transformers, what do you think about this kind of streamlined, like linear transformers or attention-free transformers? Would they work also? That allow for really long context, that not n square complex, but like n scalable, where n is a length of sequence. So that would allow for really long context.
Yeah, I mean, I guess it's it's hard to say, because usually there's like, if you can allow for a really long context but not suffer performance degradation, then that's great. And so for instance, there are these like state space models, but I think they've been really hard to like make them work in practice for these kinds of problems. So it's kind of more of a empirical question.
I actually have a kind of a related question on Muesli. Where Muesli, for example, in its Atari games, it runs for 200 million frames. Do you know how long it takes to finish a 200 million frames experiment?
It really depends on the amount of resources you know that you put it. So like Muesli runs slower than like a Q-learning agent, because it does this like world model like unroll during its update. But other than that, like, and the other thing is that, you know, depending on the network size that you use, so like the bigger network, the better. Like RL also has these like scaling laws with network size. So, but the bigger network, the slower the thing runs. The nice thing is that you can, if you have enough compute to support running many actors, and that doesn't mean that like you don't need necessarily many GPUs, or you do need GPUs or accelerators for the learner. And if you can have them for the actors, that's amazing too, because they'll just step faster. But you can parallelize actors across CPUs and then have like tons of CPUs, and then like they're sending, you know, their actions to the GPU. So if you have enough resources to parallelize acting, then it's pretty fast. I mean, it takes, you know, maybe like a day or something, like, or maybe even less. Yeah.
I see. That's cool.
Yeah, generally like there's this, you know, like when we think of 40 billion, like that's kind of what it took for adaptive agents. Like that's a lot of, yeah, that sounds like a lot of frames. But most state-of-the-art RL algorithms, like you run them with a lot of actors, which kind of inflates the data inefficiency, because it's actually like 1000x, let's say. I mean, I don't know how many actors they had, but like 100 or 1000x more efficient than that on a per actor level. You're just running many of them, because running a single stream agent takes a really long time. So like you could wait for a single stream agent for like weeks to get the same results, whereas if you parallelize, you can get them in a day.
I see. That makes a lot of sense. Yeah.
It also sounds brutally hard to do with language models, but you know.
Yeah. Yeah, I think you want to, yeah, like for language models, like powerful single stream agents are probably, yeah, are probably much more useful. But Muesli is also pretty powerful in single stream form.
I feel like in language model, you probably have less data efficiency because in like Atari games, initially you kind of start with the random policy and the data you get is not that interesting. So you're wasting a lot of data initially, but with language models, you probably get very interesting data right away, even from your initial GPT-3 policy. So if you have a large enough batch size, it should actually help you a lot and hopefully not waste a lot of data.
Yeah.
Sorry, I didn't realize. I got into a heated argument about that the other day, where I said that RLHF is always model based, but the only difference is whether it's directly model based or indirectly model based. And I think that lends itself quite well to the improved sample efficiency there.
Yeah, you mean like it's improved sample efficiency because it's kind of doing like model-based RL as opposed to model-free?
Yeah, like the language model just implicitly has a built-in world model, so it's always implicitly model-based.
Yeah, no, that's true. Yeah, I think that's true. Like, I mean, if your observations are tokens, your actions are tokens, like your vocabulary tokens, and it's learned to predict them. So like, yeah, I definitely think it's a text specific world model.
And I just saw Albert get visibly mad when I said that.
No, I totally agree. I was shocked because like I think, why was that a heated argument? Like, isn't that obvious?
Oh, I don't know. A lot of people don't seem to believe it, and every time I find someone claiming that, like an open review thing, they get yelled at by reviewers. So there isn't a paper to cite for that yet, unfortunately. There's less wrong posts, and I'll definitely cite those, but there's no paper.
Cited less wrong posts in academic paper.
Yeah. Anyway, I don't want to keep Misha here for too long. Does anyone have any last questions? Okay, thank you guys for coming to the talk. Thank you for giving the talk, Misha. I'm gonna upload it to YouTube. It'll probably be out in like a few days or something, and I'll post the link on Twitter.
Okay.
Yeah, thank you guys for coming today.
Yeah, thank you, everyone.
Bye.
Thanks for the